Start a new one. Okay. So config maps. So think of config maps as the sequel to secrets, but not as sensitive, right? The interesting thing also is that config maps can actually represent an entire file, right? So this is an easy way to inject data into pods, but not necessarily sensitive data, which is what secrets are for. Just like secrets, it's key value based. You get a key, gives you a value. Just like secrets, config maps typically need to be created before they're used, and they can be created from literals or from files or from directories, just like secrets can. They are mounted and accessed as volumes, just like secrets. The only difference is that instead of defining the volume as a secret, right, you define the volume as a config map. Now the name here is arbitrary. And then when you mount the volume, you just mount the volume, like you put the listing up above. That's it. That's all you have to do. Now here, just like you did from secrets, is that you can create it from literals, and you can put a string of literals in there if you want to. Here, by the way, you can describe the config map that you just created. Describe, by the way, is one of the most powerful commands inside of Kubernetes. It allows you to describe objects like pods, deployments, things that you've created inside of Kubernetes, and it will give you more information than you think you want, actually, about the topic. Here, we're creating it from files. So they created a file called myconfig, and they put these values into it. Execute this command to create the config map, and then you describe the config map, right? So this pod definition, right, as you can see here, is mounting a volume at etc config. Notice that it's read-only, so it can't be edited, right? And the name of it is config. And then what it's going to do is when it gets parsed, it's going to look for the name config, and it's going to define what the volume is. In this case, it is a config map. So you can apply the myconfig pod YAML exec into, like you can bash into the system, and then basically cat the config file. You can actually see the strings that you put, the key values that you stuck in there. You can see them in the system. So just remember that config maps and secrets work remarkably identical. You can also define them as environment variables, and they can also be mounted as files. Create them from literals, create them from files, specify them in your pod specification, and you go from there.
So, sir, I had a question. So as you could see, there is a dependency here between the config map and the pod, right? So ideally, your config map should exist or should have been created before you deploy the pod. Is that correct?
Mm-hmm.
So how do we ensure the ordering? Like what I'm saying, let us say you want to use a GitOps, and you have what you call all your YAML files are there. How do you ensure the ordering, or does that matter?
Well, if your GitOps, by the way, is ingesting the files as they're added, like, and there's usually some ordering structure you can make, but when it reads a directory, it's going to create the objects. And if there's dependencies, it will usually create those objects before it'll create the pod specification. So it'll usually do that last, but that depends on your system. I don't know what GitOps system. So if you're using Flux or Weaveworks or Argo CD, you can actually control the ordering dependency. But if Kubernetes gets a bunch of ingestions, it'll create low-level objects before it creates high-level pods and deployments. So even Kubernetes itself will typically, if it parses an entire file, it'll create the objects that it needs to first, which is the low-level objects, before it creates the high-level objects. But you can control that inside your CI/CD system as well.
I wonder if that customized could help to do like an ordered deployment. If I specify, I customize which part, which objects gets created first.
I don't know, actually. Yeah, I haven't used
Yeah.
customize enough to know, but like I said, Kubernetes itself will actually do low level
Do
objects
that.
before it. But if you need
Okay.
to be explicit about it, yeah, I'm sure you could actually do that in customize. I haven't done that myself, and I haven't seen any parts on ordering, so I don't know if it does. So I don't know. I don't know about customize.
No.
Yeah, but like Terraform, which is another thing that uses like YAML, well, uses HCL files. Even though it ingests a bunch of objects, because you could put every single object in your deployment into one file, it's going to create certain things first before it creates other things. Now, I don't think you can control that very well, unlike you can with Terraform, but maybe customize is the answer. But what I usually do is just get the CI/CD tool to look at those orders first, right?
Gotcha. So you mentioned that in the same file. So sir, is it common to use just one YAML file where you have the definition or specification for a deployment as well as corresponding service object?
No, it's
No.
common for you to have a single file for every single Kubernetes object that you're going to create, even if it's all in the
Okay.
same directory.
Gotcha.
Yeah. That way, because remember, we're trying to get our changes to be batched as small as possible, especially for GitOps,
Yeah.
right? And so what we'll do is every single object will have its own independent YAML file. That way, if you update that file, it is a very discrete change, easily checked, easily tested, right? And if you try to start a pod specification like this, and the config map doesn't exist, it'll throw an error, say, hey, the config map doesn't exist. So. Although I've seen that, I think they were going to change that behavior in 1.24, but anyway, yeah. So any other questions about config maps? Okay. Okay. Kind of more of a security thing, but just kind of giving you a preamble before we get to it, is that a security context is basically where you tell Kubernetes how you want the pod to run. In other words, what user is it running as? What group is it running as, right? So it's not just the application inside, right? But it's like the container itself, like what are its permissions and limits? What file system group does it have access to? Those are like really common. Security context can be set inside of the pod specification that basically says, hey, I want this like in particular container. Here's the security context for this entire like pod, right? So in general, people are moving away from using the root user and they're asking you to specify users. Now, how do you know what the user group and all that other stuff is? Usually an administrator is going to provide it for you, or they're going to, as part of the CI/CD process, they're going to inject it into your pod specification or your pod like launch, right? So users and groups mainly revolves to how processes are executed. FS group relates to what file system permissions you have. So and that's just part of the pod specification. So we'll talk more about those kind of things when we get to security. So that's just a little preamble of what's there, right? Do note that when you roll out a deployment, whether it's a deployment, a stateful set, a daemon set, or a cron job or a job, those are the 5 workload types. Notice that it can have like states of like, did we roll out? Like, are we progressing? Did we complete, or are we failing to progress? You can actually see the rollout, which is like the update or the like updating of an image or the rollout of an image, just by doing kubectl rollout status and then just put the deployment name, and it will basically list the deployment status for you. Replicas, we've mentioned before, you actually saw me edit replicas the other day using the dashboard, is that this allows you to turn the dial on the number of instances of a single application pod. So if you want to add more pods because you have 3, you want to go to 5, you can. You want to go from 5 to 4, you can, right? You just need to change the replica value, And the replica set will then see that the value is changed and enforce that change among the application in question. Scaling, by the way, is basically all it does is it's just changing the replicas. Because remember, it's horizontal scaling. Now, there are vertical pod autoscalers or vertical pod scalers that will allow you to upsize resource definitions on a pod as needed. So not just horizontal scaling, but out of the box, Kubernetes will do horizontal scaling. If you want to add the vertical pod autoscaler, it will actually upsize the pod definitions as well as far as their size. Because remember, you can actually set hardware limits for a pod specification that says each pod can't take more than 2 gigs of RAM and 2 processors. If all of a sudden a single process needs more, there's ways to set that up to where it will allow you to increase the limits programmatically up to whatever mins and maxes you specify. So it won't just like increase it for the world, but it will allow you to go up to whatever limits you're like, I'm okay if this thing takes 10 gigs of RAM, right? So you can actually you can set that as well.
So we heard that there is a Kubernetes auto scaler, something like that, that adds that might even add additional worker node to your cluster. Is that correct, sir?
Yeah, so that's the not the horizontal pod autoscaler, but the cluster autoscaler. So you can actually set a cluster autoscaler.
Oh, cluster autoscaler. Gotcha.
Yeah.
Gotcha.
Yeah, the cluster autoscaler will actually expand and contract your worker nodes based on what your like pressure is, like your specifications.
Gotcha.
So there's on top of the virtual machines, there's a horizontal pod autoscaler, which will add more pods if necessary. Right, so that's just scales pods in and out. Then there's the cluster autoscaler, which will actually scale and add more worker nodes to your cluster if needed.
Gotcha. Gotcha.
Most people run both. And by the way, the cluster autoscaling will actually talk to autoscaling or scale sets or whatever you're using on Google to actually add more nodes to your autoscaling group or your cluster, your VM scale sets as needed. So it actually will leverage the cloud provider's options for that. It won't just do it natively.
Makes sense.
Yeah. This is just you manually scaling the pods yourself, right? Using kubectl scale deployment. Now, notice, by the way, unlike some other commands that you've seen, you have to declare the type of object that you're messing with. Note that that says kubectl scale, and then it says deployment, and then you're going to put the deployment name, and then you're going to put the number of replicas. So some of the commands in Kubernetes, all of them, by the way, will take this. You can actually declare the type of object that you want to manipulate right before you put the object name. Usually there's a slash in front of it if you want to do it. So you can actually munge them together if you want to. The reason I mention that is that it's often good to be explicit because sometimes things will end up with the same name except for the pods. So sometimes it's good for you to declare the object type that you want to change instead of just leaving it for chance. So notice here under the example, they are scaling the Nginx deployment to 3 replicas. And then here, they're basically setting an auto scale command, which is a relatively new feature that basically says, hey, look, if Nginx basically goes above 50% average utilization across the entire set, I want you to scale to a maximum of 6 and a minimum of 4. So this is a pod autoscaler that's included with Kubernetes. And I believe you can set multiple dimensions for that, like you can set memory pressure and CPU pressure. If you ever want to update a file, a deployment, you can just update the YAML file that you originally used and just reapply it. You don't have to type a reapply command, just use the apply command, but it's run the command again, right? So for example, you can update an image, you can increase and decrease the number of replicas that you have, all pretty straightforward. So if you have a YAML file that specifies 3 replicas and you update it to 5 and reapply it, it's just going to scale it up to 5, right? So the update policy is usually listed inside the pod specification. If you don't specify one, rolling update is what it usually does by default. So I don't think there's anything else I wanted to mention there just yet. So in this chapter, we basically talked about the different volume types, persistent volumes and persistent volume claims, and storage classes. We talked about dynamic provisioning, which doesn't require persistent volume definition. We then had a discussion around secrets, storing sensitive information, and how you can mount those environment variables or as a file on the file system inside the container. Same with config maps, except not base64 encoded, just plain text. And then we talked about security context briefly as the ability for you to set a context for a pod to run as a particular process, group, and user, or as a file system group. And then talked about like, how you can use rollout to actually check on a deployment status, how you can actually turn the dial on replica sets using either the changing the replica value or using the scale or the auto scale command, right? And then just that when you do an update, it is typically a rolling update and you can update the file. That's usually the best practice, is to update the file and then reapply it in order to get it to function. So that's what we covered in chapter 5. Any questions about any of that? Any curiosities?
So for this rolling update, so if in the deployment YAML file, if I change my image tag to something else, will it then create a new instance of using new image, and will it automatically delete the old part?
That's exactly right.
Okay.
That's exactly what it will do, is it'll usually add a new one, delete the old one, and roll new traffic to it, and just keep doing that until all of them are replaced, right?
Mm-hmm.
So it'll just keep dropping and adding instances. The reason that's cool is, especially if you have 2 or 3 or more instances, is that traffic won't get routed to the instance that's getting replaced. So you might see a blip for like half a millisecond, but traffic's going to go over to the new systems. Running systems, whether they're new or old. So it literally will just replace them one at a time. If one of them hangs, it'll stop the deployment, right? It won't actually finish the replacing if one of them doesn't come back up. So it's kind of nice. Okay. Before we go on to chapter 6, first of all, let me check. Oh yeah, it's actually been an hour and a half. So let's take actually a little break here before we keep going forward. We're gonna pop into chapter 4, design, and then we're gonna spend some time looking at labs. So we're gonna spend probably another like 30 or 45 minutes talking about design, and then we're gonna spend 45 minutes working on labs. So let's take let's say maybe like a 15-minute break. So let's come back at 46. So just 1 minute after the quarter of the hour, right? So 11:46, we'll come back. I'll put up a timer. All right, welcome back, everybody. So, I'm gonna just share a little something. I went back and looked at the design section, and we're gonna cover it, right? But when I looked at it, I realized that there's no section in here about workloads, which I've literally mentioned like 3 or 4 times. So I'm actually gonna rope in a section from another class and pull it into this section. And then I'm gonna give you the PDF for the other class. Now, I know that sounds weird, but I feel like there's a deficiency in the class. I actually already talked to WebAge, and I was like, I'm just gonna give you the other class as well. So I'm gonna post the PDF in here in the Zoom chat here in just after we get done with this section. So you can have access to the information I'm about to talk about, because I told them and they agreed that there's actually a missing section here on workload management, that you should really know about just so you can understand the different deployment types or workload types inside Kubernetes. So everyone okay with that? Just letting you know. I heard a click. I'm gonna take this yes. Yeah.
Oh, that's by accident.
Oh yeah, no worries. Yeah, and the other class is actually contains pretty much everything we covered, including Docker introduction to Kubernetes, the Kubernetes architecture, and it also includes the workload management and then scheduling and logging, which is just really just general statements about how the scheduler works and how logging works. I'm not necessarily going to cover that per se, unless you really want that, but I'm definitely going to cover workload management. So I'm going to give you the PDF for this because I want you to have it in your toolkit in case you need it. Okay. So let's talk about workloads, and then I'll talk about like section 4. So workloads, as you may remember from the dashboard, workloads are basically objects you use to manage and run your pods and containers on the cluster. So to deploy and manage your containerized applications, you basically create these like meta objects around the pods, which the pods are themselves objects around the containers. So without this, what ends up happening is that you end up having to create all of the associated Kubernetes objects yourself, like replica sets and whatnot, in order to do that. Why? Let's just actually like leverage what we've got, right? Let's just leverage the system that will actually create all those objects for you. Now, the different workloads are used for different purposes, which is why they exist. And you can actually create your own custom workload types in Kubernetes just by extending the API. Where's my mouse? There you are. Weird. All right, so for example, like, let me blow this up for a second. So not a deployment, not a stateful set. The way this works is that when you deploy, for example, I'm just going to throw one out there. Let's say that you're deploying a daemon set. Now, daemon sets are really interesting because when you need to run a pod on every single node, no matter whether that node is added by you or added by Kubernetes or added by AWS, any node that's part of the cluster, if you need to make sure, for example, that every single node has a logging agent on it, you're going to use a daemon set. If you need to make sure that every single node has a security scanner on it, you're going to use a daemon set. So daemon sets ensure that every single node in the cluster has the software in question. That is one type of workload, is a daemon set. Now, if you run a stateful set or a deployment, which is two other types of workloads, and you can literally see them in the dashboard, these both use what's called replica sets. And these replica sets basically ensure that you have a certain number of pods running across the entire cluster. So the other two deployment types, which are not listed here per se, deployments and stateful sets, but they are in the text, so we will talk about them in a second. These, all they do is they basically allow you to specify a number of systems, and it's across any like combination of the actual nodes here. Now, one thing to note about stateful sets is that stateful sets has different from deployments. Stateful sets keeps the pod name the same. I know this is a little weird, but if you notice when we were looking at our Nginx installation yesterday, there were 3 pods there, and they all had these funky alphanumeric names on them. If you use a stateful set, those names stay the same, even if you stop and redeploy the pod. In other words, if it's MySQL-0, MySQL-1, or MySQL-2, as long as you have 3 pods, you are going to have those three names. So stateful sets keep the names consistent, whereas deployments do not keep the names consistent. That's really the big difference with stateful sets, is that the DNS name or the pod name doesn't change even if the pod is restarted. With both deployments and with stateful sets, you can add storage. With daemon sets, you can add storage. With jobs and cron jobs, you can add storage. So stateful sets, for example, don't have a claim on persistent storage. The thing that makes them stateful is that the pod name can always be found the same inside of DNS or service discovery. So deployments and stateful sets are by far the most common type of deployment types. Daemon sets are used by operations and security folks or networking folks. Jobs and cron jobs are the most rarely used, at least from my standpoint, job types inside of Kubernetes. The difference is that a job, also known as a batch job, is used to kick out processing across parallel systems for a one-time run. Analytics, number crunching, reporting, it's a one-time run where you want to maximize it across the entire cluster, runs it across the entire cluster set. When it's done, it returns a result, you're done. Not for persistent running workloads, right? Cron jobs are just jobs that run on a time-based scheduler, and they don't run persistently either. They don't run 24/7. Daemon sets, stateful sets, and deployments will all run 24/7 if you let them. Jobs and cron jobs, a job will run until the job is processed. A cron job runs based on time and will also run until the job is processed. Once the job is done with a job or a cron job, once the job is done, it's going to shut down. That's the difference between a job, cron job, and the other sets. Is a daemon set, stateful set, and deployment is for a persistently running application. Now, to dive in this to a little bit deeper, let's pull that back just a little bit. So you can't actually create workloads in three ways. We've already seen this, by the way, right? We've seen the imperative commands, right? Which is where you basically use create deployment, right? We've seen declarative commands because we've pulled in a file, right? Where we applied a file, right? And we've seen the configuration file that we've used because we've seen that in the YAML that we've pulled in, right? Do note, by the way, that the API versions do change on Kubernetes. So every once in a while, it'll say something like, hey, by the way, you're using beta, we're now on regular, or you're using alpha, and we're now on beta. It'll tell you, by the way, when it sees that. So you just need to know that if it complains about the versioning, you just need to go and look at your Kubernetes installation to see what version it's using. I just want to be clear. I don't know that it goes like, I've seen it go from alpha to beta to not. I haven't seen it go from like version 1 to version 2 yet, right? If you're on your installation, by the way, and you need to find it, wonder why that reset itself in size. That's weird. If you're on your installation, okay, there's all my stuff. Okay, we're good there. Oh, what's that doing? All the metric servers crashing. That's weird. Anyway, if you're on your server and you ever need to find the version of the API that you should be using, just run kubectl API resources. What this does is that this will tell you, God, there's a lot of Rancher stuff in here. Did I haven't mentioned, by the way, that Rancher takes over a machine? Notice that in here, by the way, you can actually see the API version listed here, right? Apps version 1 for deployments, daemon sets, replica sets, batch version 1 for jobs and cron jobs. So if you need to check your version, just type in kubectl space API-resources, and that will tell you the version that you're running. Like I said, notice that none of these say version 2 yet. Do you see version 2 out here? But I've seen them go from alpha 4 to alpha 5, or from beta 1 to version 1, right? Notice that there's a bunch of Rancher stuff out here. So I got Rancher installed in my cluster. I'm sure those of you who are using Rancher are used to this, right? There's our KE. Oh God. Moving on. Notice here that the K8s ones are still either version 1 or version 1 beta 1, right? So yeah. Huh. Interesting. Unable to read metrics K8s. Huh. I thought that was short. Anyway, having a problem with my cluster. I'm gonna have to go troubleshoot and find out what's going on. So just know, this is what you put in the pod specifications or the object specifications for your files. It'll be pretty intuitive if it finds a problem. Oh, here it is. kubectl API resources to find it, right? Okay. Now, one thing that's clear is that you're going to be either running stateless and or stateful applications. Stateful applications are data stores or other applications where you need to persist the data. Stateless applications are where the session state and other persistent information is not kept inside the system. Here's a sample deployment file. You've seen this before, right? This has 3 replicas. It's running Nginx 1.10 as the image. You've seen this without all of the preamble, the commentary inside the system. There's the container board, right? Meaning containers listing on 80. When you work with deployments, you've already seen apply and getting deployments and getting pods. You've seen this already in your lab, right? Where you've basically described and seen the pieces. Now, some of this you haven't seen because this is a different class, right? But we talked about scale, we talked about rollout, right? And I am going to share this PDF with you so you can have this on hand. But any Kubernetes cheat sheet is going to have this available for you to see. Now, stateful applications are things that have to retain state, whether it's a data store or some kind of session driver or an in-memory cache, which has persistent backing. A stateful set is typically considered to be the deployment type, while stateless applications are supported by deployments. This is all in the Kubernetes dashboard. So if we go look in the dashboard, and let's just set our namespaces to all namespaces, just because, like, why not? That's going to drive me crazy. I'm going to find out why that's failing. If we go up here and we look at the workload types, notice it says deployments. If I click on that, by the way, it's going to show me all the deployments that I have. I can look under stateful sets, of which I don't currently have any stateful sets because I don't have any databases on my system. And then I can then look under daemon sets, which I have one called kubeproxy for that system. And then I've got cron jobs, of which I don't think I have any cron jobs, which I don't. And the last is jobs, which I actually do have some jobs. These are all part of an admission controller for the ingress controller that I have running on my system. So I'll talk about ingress controllers when we get to services and exposing applications tomorrow. Okay. Remember, ingress controllers allow you to do things like this. Oh, I forgot Google. You always take that over. Hold on. Richard.local dev. So what this does is I can type a name into my system, and if DNS will resolve it correctly, I will then get redirected by an ingress into a system. This is not a workload type. I'm just letting you see the service really quick, right? So this is how I get to Rancher. Interesting. So stateful sets are for applications that you want a consistent name for the pod. To be clear, with both deployment workload types and stateful set workload types, you can attach storage. So you're not limited to just using stateful sets to attach storage. You can attach persistent storage technically to almost any workload type if you want to. Okay. Here's a stateful set manifest file. Looks remarkably like a deployment type, and the only difference is really this volume claim template. But let me restate this. We have seen deployment files that have persistent storage attached to them. Storage is not the differentiator between deployments and stateful sets. The difference is that the naming of the pods doesn't change with stateful sets. with deployments, it will rotate. All the stuff that you can do with deployments, you can do with stateful sets. The naming is the one thing, like I said, that stays the same. Everything else applies. Rolling out, scaling, changing replicas, looking at the persistent volume claims, looking at the persistent volumes, looking at the services. There's no distinction other than the naming. Jobs, which are different than deployments and different than stateful sets, these are execution based. So they're going to run distribute across the entire cluster, or however many number of parallel jobs you set. And then once it's done running its execution, it's going to stop. Here's an example. This is a batch job, or also known as a job. And what it's doing is it is calculating pi, I think, to 2,000 places. That's a lot. Not obviously not as far as it can go, right? Notice that it's going to run 5 parallel instances of this calculation, and it's going to take 100 seconds before it's going to kill it, right? So it's only going to allow it to run for 100 seconds. So it's actually got a time constraint on it. And all it really needs is one full completion. In other words, they only need to run it one time. It's not going to restart, right, once it's done. Notice it's using the Perl image latest because there's no tag on it, right? Completions is optional, right? By default, when a job completes, it terminates the pod. You can specify the number of times that the operation should be completed before the pod is terminated, right? Deadline is a deadline. You kind of know that. It'll wait indefinitely for the operation to complete if you don't actually specify a deadline. And parallelism says, you know, how many of these jobs can I run simultaneously at one time? So what this means is that you can have actually 5 instances of this job running simultaneously in the background. Same things apply to basically a job as they do with a stateful set or a deployment. The catch here is that this job is only going to live for as long as it takes for it to run. Once this job is done, the pod's going to shut down, right? So these are usually triggered as batch files that get pushed onto a Kubernetes system. They're usually triggered by some kind of trigger. So you can describe it, you can scale it to bigger, you can delete it, right? Now, daemon sets, so we talked about a little bit about deployments because we saw that a lot of that, stateful sets, and then jobs. Just to mention this, cron jobs work the same way. The only difference is that you have to put a specification in here about how often the cron job is going to run. And it's a cron job field, actually. I don't think cron jobs are listed here. So let me just take a minute, go off the rails a little bit. So here's a cron job, and here's an example. See this schedule right here? So the job template looks remarkably like anything that you would see in a deployment, but notice the kind is job, and then here's the schedule, right? That's pretty much going to run what? Every minute, right? So it's going to print hello from the Kubernetes cluster every minute. Cron syntax, by the way, follows standard Unix syntax or Linux syntax, right? So this would be like yearly, monthly. You can use like a cron generator, like crontab.guru if you want to peel that back. If you want to see like more detailed about running automated tasks with cron jobs, here, by the way, is Katacoda and Play with Kubernetes labs that you can kick on. But here it is running the same thing, echo hello, right? You create it, and then you can get the cron job, and then every minute it's going to run that whole thing. And then you can watch the job if you want to, right? If you want to see like how many jobs has it run, right? Note that the job name and the pod names are different, right? Because these pods are going to have different names every single time, right? You can actually do the pod log if you want to like find out. Notice they're using a selector up here to actually find a particular job name pod, and then they're running logs against that pod name. Then you can delete a cron job if you want to. So all of that works just like it does for anything else, right? You can get logs for it. You can delete it. You can't really scale it because it's just going to run one instance of it. So it's not like a batch job. But just know, right? Deployments and stateful sets are used for persistent applications. Jobs, which are really batch jobs, and cron jobs run into completion or run on a schedule. And then last but not least, we have daemon sets, right? So daemon sets allow you to deploy one application pod of this type per node in the cluster, worker nodes, right? So here you've got one worker node set per cluster, and that's its function. It's just to make sure that we're keeping the daemon sets on each particular node in the cluster. Here's a sample file. In this particular case, it's just like, it looks like it's echoing that it's running on a host name. So you can see it in the log files, and then it's sleeping for 10, and it's just continually looping around. It's actually using Ubuntu Trusty to do this job. Most of the time you don't see stuff like this. You see Elasticsearch like Fluent D, or you see some kind of like scanner, like a tripwire scanner or whatnot running on the system. What else is in there? Security scanning for like containers, like you'll see like Stack Rocks, for example, out there. Notice the kind says daemon set. And then we talked a little bit about rolling updates. This has like a much deeper like rollout status. And this actually gives you something that you can run inside your system, where basically you're setting it to 1.9.1 for Nginx. And then you're actually rolling it back to like a different revision if you want to. So, and you can also set resource limits if you want to, and requests. So there's a couple of good, like really good commands in this this document that you can use to play around with. So if you forget to set it inside the file, you can actually go back and apply it. This can actually be good as part of a CI/CD pipeline as well.
So the opposite to roll out, is there a like a rollback option?
There is actually.
Mm.
So you can actually undo a deployment. You can actually specify like that you want to roll back to a particular revision. So when you do the undo, for example, you can say, I want to roll back to revision 4 or revision 2 or revision 1, right? So you can actually roll it back to the previous deployed version. If you need to see the history, you just do the rollout history command, right? Notice here that it is actually specifying the object type. So it's specifying, just like the scale command, it is specifying the object type. You can do that, by the way, with every command just to get into the habit. It's probably good practice because you're going to need it with some commands and not need it with others. And it gets really confusing, frankly. Okay. So that whole exposition was just to get you familiar with the different workload types. Stateful deployments, stateful sets, jobs, which are batch jobs, cron jobs, and of course, daemon sets, which are really kind of more administrator types, but still useful. So I'm going to share that 2919 with you. Hold on just one second. Where did I put that thing? Let's see if we can find it. Here we go. I'm going to post that into Zoom so you can download it for yourself. But that is the bigger version That's actually part of the Tech Excellence Cloud Engineering program. So for those of you taking that already with me, you already have a copy of that, but just want to make sure that for those of you who don't, you have a copy of it. The chapter we just went through is actually chapter 4, which is the Kubernetes workloads. I just wanted to make sure that you had seen that. Okay. All right. Let's talk about design just so we can say that we covered it, and then we're going to roll into a lab on deploying to Kubernetes. Okay. I'm going to be mindful of time here. So this is actually just going to be a quick skim because you've seen this already. So we talked about how traditional applications are run inside of an operating system on a virtual machine. Obviously, in this case, we've talked about like where the kernel lives and where the app is living and all these other pieces, right? And the problem here is that every time you scale or create a new instance of that virtual machine, you're also copying the operating system and the licensing, which the containers don't do that, or they don't have to do that, right? It's not a requirement. Containerized applications really just need the application and any associated libraries. You don't actually have to stick an operating system in there at all because it's not required for the container to run. Now, one thing that's actually very interesting is that both storage, memory, and CPU are typically decoupled in a containerized environment because it's abstracted away. Doesn't mean you don't require them, but compute and memory typically run on the host and storage runs on a separate system, right? Typically, you don't use storage on the local host, and that's true in cloud as well, actually, even for virtual machines. But for containers, that's doubly true. That way you can move containers around to different hosts and they can still get access to their storage because the storage is on a network backend. Now, containers by their nature are transient. It's the volumes that are permanent. So containers will actually get restarted. Now, this is not always great for like RDBMSs, for example, like Oracle or MS SQL, because even though it'll recover, that means you've interrupted any persistent database connections. With a NoSQL system, this is also true, like a MongoDB or an Elasticsearch, but less true because any other system can actually pick up the connections and there isn't necessarily a connection loss at that point. So just know that containers are considered ephemeral. They are very transient, and Kubernetes will move things around as needed, but only as needed. It won't just move things because it like wants to. That doesn't even exist, right? And this is just kind of an expose about understanding that applications need to be flexible. They need to scale differently. They need to use different frameworks, right? But containers, this is just like understanding that a flexible framework is needed, which is where containerization comes in. Now, resource usage is something we've like talked about technically, where we put resource limits inside our files or we put it on the command line. We literally just saw this with Nginx, where we specified a resource limit and a resource request. Now, in this particular case, allocating 3 gigs of RAM to an application that only ever uses 1 obviously is going to waste it. So we talked about using the bad actor system where you actually performance profile what an application actually uses on a per like user basis, and then scale it against whatever like limit is the most efficient. Measuring resource uses, like I think someone was mentioning the use of JMeter. There's a number of tools that can manage the performance of an application. Fingerprinting and measuring the performance of an application can be pretty important for running a Kubernetes cluster. But the cool thing is that with mixed workload types, you can usually find some efficiency because application A is going to be busy a couple of days while application B is going to do nothing. Application B is going to be busy on days that application A isn't really doing anything. So you can use Docker stats. You can also get some Kubernetes stats. Kubernetes actually works really well with something like Prometheus and then using Grafana for presentation. Prometheus is a metric server that even AWS, for example, runs as a managed service that you can actually use on your Kubernetes clusters to get information. So just know that you do want to be gathering things like what's the disk usage, what's the network usage, what's the CPU usage, memory. for your applications. By default, containers have no resource constraints. That's true in Kubernetes as well, not just Docker. Just know that you can, just like you can in Docker, where you can set resource limits, you can do that, all of that in Kubernetes as well. Okay. This is just a little bit more about label selectors, as far as like using label selectors to match against environment, Windows type, GPU, present, not present. We have talked about this already, but it's just like basically saying, hey, where, I'm looking for this key equal to this value. So we have actually looked at this at the same level of detail. You can do it based on role as well. Like if you have where environment equals, dev QA staging versus like prod 1, prod 2, prod 3. So these are all actually just stuck in the pod specification. And then we already talked about multi-container pods. But here's something that we haven't really talked about. When we talk about injecting inside of a pod a sidecar container, what we have is we have a container that has access to the same resources as that application container that you see there. And that sidecar container is either going to intercept networking requests, intercept disk requests, or it's going to read the networking in parallel or read the disk in parallel, like, on the side. This is a sidecar container who is usually solving some kind of security, operational, or networking problem. And it's going to sit inside the same pod. So it has the same networking stack, same memory space, etc. So what's the use of a sidecar container? Well, for example, if you want to enable a service mesh, which means you want to intercept all networking connections and do some controls against them, that's going to be a sidecar. You want to read all the log files inside of the same pod, that's going to be a sidecar. You want to do a security scan while the pod is running from inside the pod, not outside, that's probably going to be a sidecar. So the sidecar uses are practically infinite as long as you want to be inside the pod with the main application container. So for example, sidecar containers that implement additional ways to access the main application are sometimes referred to as adapter containers. It's just a variation on the sidecar container. When you run a service mesh, for example, all of the network traffic actually comes in and hits the adapter container, which is the the Envoy proxy. And that Envoy proxy will then, feed the networking information out to the main application. The main application will respond through the proxy as well. That's sometimes referred to as an adapter container, but it's really just a variation on a sidecar. So all of that, the workload management and the summary, was basically just to highlight that there's a number of different ways to run your containers. You can manage your resources by setting limits and resource requests. You can actually access labels either as an equality set or picking out of an array of values. And most of this actually we've seen in some form or fashion before. It didn't necessarily go deeper, which is why I skipped it yesterday. All right. Let's get into this because this might be pretty fun actually. So in your lab guide, what I'd like for you to do is we're going to spend some time working on lab 4, which is actually going to take place in the WA3007 machine, which is the same machine you started yesterday. We're pretty much going to stay in that machine, if I remember correctly, for the remainder of the class, so you don't have to worry about shutting it down. Same thing here as far as you're going to set it up. You don't have to close the terminal. I did ask them about that yesterday. They were like, yeah, we probably just need to remove that instruction. But you're going to make sure your cluster is start. You're going to deploy a custom image, get your pods, get your services, expose some things, and then you're going to access the sample Spring Boot application. Wait, did we do this one already? Stop me. Did we do this already? Or am I just having flashbacks from a previous class?
I don't think we have done it.
Yeah, okay. I'm probably just having flashbacks from a previous class. I apologize. So let's do lab 4, and then deployments, view and run logs and containers. And then, by the way, here's some exec. So you're actually going to be able to execute some commands inside of a running container. And then you're going to delete the service and the deployment, get the deployments, etc. There is a YAML file in here that you should already like have access to, which you can then change and comment, play with the replicas, etc. And that's pretty much it. Then there's the cleanup, and then you review it and you're done. So we've got about 35, 36 minutes left to do this before we stop for lunch. This is considered to be a 30-minute lab typically. So let's take a run at it. While that's happening, Vinod, I think you and I are going to look at another lab while everybody else is finishing lab 4, correct?
I said that would be greatly appreciated if I could do it.
Yeah, let's go take a look at it. All right, everyone else, go ahead and start and finish lab 4. Once you're done, we're going to break for lunch at 1 o'clock. So just come back at 2, and then we're going to cover security, and then we'll do a security lab. All right, Vinod, I'm going to stop my sharing. A couple of interesting things to note, right? Is that, of course, we have to make the statement that, security is obviously important, particularly for production deployments, but even in non-prod, it can be useful. Security for Kubernetes is a little harder simply because we are not familiar with Kubernetes as much as we are with like virtual machines. That's just a kind of industry exposure thing. Now, as part of securing a deployment, a lot of it revolves around access and then actual like defending and securing the network traffic for Kubernetes itself. So who has what to like control and set things up inside Kubernetes? And then how do we protect data at rest and data at transit inside Kubernetes? More data at transit, right? What does that look like? What are some networking things we can do to improve security? Now, we talked about how the API server is pretty much the central like access point for every service to talk to every other service. So it's a gateway to the platform. The kubelet, the scheduler, controller access, etcd access, this all goes through the API server. So most of the resources are represented as a string. Looks exactly like accessing almost any other API. And then usually like either a sub resource for the object, potentially a name, and then resources under that. So for example, in this like thing they have here, someone's doing a read against API version 1 against a particular namespace against a particular pod, and they're trying to grab the logs, right? And if you have authentication or anything authentication is disabled, then executing this like has a curl or a wget or whatever would actually work. Now, both the CLI tool and the web portal also all talk to the API server. So any call made into the system is going to have to go through the API server, which sits on the master, right? So before it is executed, it has to be authenticated. Now, this uses certificates based on X509, basically certificates, right, to secure and encrypt the traffic. The certificates and the client certificate information is stored in the kube config in your home directory. So if you go to kubectl config view, this will actually show you what clusters you have set up in your system, and then all of the security context that you have, what your current context is, and any other kind of like user definitions and user preferences in here. Now, as you can see, I have a user section, which contains the Minikube like user. Then I have a Minikube context, and then I have a Minikube cluster. So I'm using Minikube inside of a virtual machine. And so this is the IP address of the server and the port that we're accessing it on. Notice, by the way, it's a 1.24 system, at least for Minikube, right? So, and then notice that here's the location of the cert in question for the certificate authority. The reason this is significant is that, excuse me, down here is the user. this user is defined by this client certificate and this client key. This certificate in particular needs to be registered with this certificate authority in order to get access to this cluster. Now, this context, by the way, sets the minikube context, which in turn says that this is the cluster that I want to talk to. What's the name of the cluster? Well, its name is minikube. So this cluster context says, I want you to go to this cluster. When I execute commands, what's going to happen is it's going to grab this minikube user, because that's what I'm using is the minikube command. And that minikube command is going to talk to this certificate store in order to access the one that's named here, right? So just know that this shows you the entire context of not only the clusters that are currently active, but ones that you could switch context to. In other words, I could have multiple clusters defined, multiple users defined, and multiple contexts defined. The one that's active is the one that's listed right here. That's my current context. I am set at the minikube context right here. Right? So my current context actually matches this. Okay. Now notice that there's a user defined here, which is obviously points down here, and there's a cluster defined up here, which points up here. So the context really says, hey, I need you to look at these two things. Now, the reason this is significant is that Kubernetes does not actually use a user database, right? It uses a certificate authority, which has client certificates registered to it. Those client certificates have the name of the user, in this case, minikube, in the subject line of the certificate. So be aware that that works a lot differently than most other systems, which of course have actual username, passwords, fields, that kind of thing embedded in them. One thing I was going to check on was, hold on. Don't do that, sorry. Oh, let's see. 1.22. Oh, cool. Okay. Servers 1.21.7. Okay, cool. Just wanted to check really quick. All right. So kubectl config view will give you that whole context that we were just looking at. All that really is doing, just to be upfront about it, is that if we actually go into my home directory under .kube, you'll see right there, if we cat config, it's the same thing. It's just literally just showing a view on the config file. What's commonly referred to as the kube config. I don't think anything was like edited out or anything. Although this is a little bit more YAML-y. It is YAML-y. It's YAML-y. Okay. This kube config, here's another example. Here we have the context. Sets the current context. Obviously, here's the keys and the CRTs that we're talking about. Same thing that we just kind of peeled back. Now, the CA-CRT represents the certificate authority that is used by the cluster to authorize access. You are granted a key and a CRT, right, that maps to the user minikube, which, by the way, in this particular case, is the default cluster admin. kubectl is going to use both the certificate and the key to encode the request that you're making with kubectl, which then gets authenticated and then lets the command run. So just remember, there's a .kube directory, and then there's a config file, and that should have configuration information about where to find the keys, the CRT, and the certificate authority for the data store you're trying to connect to. This, by the way, works whether or not it's an Azure Kubernetes cluster, an EKS cluster, a GKE cluster. It works this way regardless. There are other ways to authenticate, but this is the one if you're doing kubectl raw access out to a cluster. Now, when the API gets hit first, it authenticates that you are who you say you are. How does it do that? Well, it uses a certificate that then validates against the certificate authority. Once the certificate authority says, yes, this certificate is valid, it says, okay, well, you're Minikube. Awesome. What can you do? That's where authorization comes in. It says, what do you have permissions to do? And then the admission controller checks and allows you to do the things you want to do against the Kubernetes objects or resources that you have permissions to do so. So after the request gets past TLS, it's going to pass through the authentication phase, right? And it's going to basically like look at the, like, how do I know who you are? Now, in this case, once you pass TLS, it actually looks at the subject line and says, hey, this user's Minikube, right? So the client certificate, the CRT, right, is the most common method by which this happens. But do note that Minikube can hook into third-party systems, which we've talked about, like OpenID, GitHub, LDAP, Kubernetes, Kerberos, like all kind, yeah, you get it. And then after you verify who is this person, are you who you say you are, for authorizing a request, it's going to look at the username of the requester. It's going to look at the action. It's going to look at the object, and then it's going to evaluate its policies to see if the user is allowed to do the thing that you want it to do. By default, a user can do nothing against an object unless they have been granted permission to that object. So authorization is based on one or more modules. So authentication has its own authentication modules. Authorization also has its own modules. Here, there's role-based access control and attribute-based access control. Attribute-based access control basically says, look, we're going to give you permissions to the users through the use of policies, for example, that combine different attributes, right? So there might be one object listed per line that says, hey, you're allowed to touch this particular object, this particular attribute. So you might say, hey, well, we're going to add, for example, this says Minikube start extra config, and this is actually enabling attribute-based access control. And then in this policy, it says, if it's this object, if you are able to touch it, like based on different attributes. If we look at the documentation for this inside Kubernetes, if we look at this, it says there's one JSON object per line. There should be no enclosing list. Let's go take a look at this, right? There's an algorithm, right? So this is an ABAC authorization. Here's the policy, and here's the specification. The user Alice for this namespace in any resource can do anything right in these API groups. Same here with attribute based, right? Policy. Kubelet in any namespace can do anything through the pods. Well, I can actually only read the pods. Right, this is where you're like setting attributes. Right, and so there's lots of different options for this where basically you're setting attributes, resource paths, read only, right? Here's a complete file example if we want to see it. Variety of different namespaces, right? User, scheduler, kubelet, whatnot. And then here's the resources they can touch, and here's the APIs they can talk to. Right? Notice here that they've only got read only. But here they can do practically anything. Well, they can't do anything, actually. And then if we go and look at RBAC, which is by way of comparison, using RBAC authorization, this basically is regulating access to the system based on a role that is assigned to the user. So not just the attributes that have been declared inside of a policy, but does the user have this role in question assigned to the user? So one is more focused on the resources, right? And one is more focused on the user identity. So think of it, it's almost like with AWS, it's almost like the difference between identity-based policies and like resource-based policies, right? And so in this particular case, if someone doesn't have like a role or a cluster role or some kind of cluster admin role, for example, right? you know, for example, here's a cluster role. So we're going to call this the secret reader. And what happens is that for the secret resources, someone gets these particular verbs, right? And then what happens is that you then bind the role to the person. And you use, for example, if it's a role, you use a role binding. If it's a cluster role, you use a cluster role binding, right? Which should be fairly intuitive. And so in this particular case, this is a role binding. And then what they're going to do is they're actually going to take the read pods in the default namespace, and they're going to assign it to the user Jane, right, from this particular API group. Here's another role binding, read secrets, namespace, Dave, cluster role. And then here's a cluster role binding, read secrets global. This is a group actually, bound to a manager. And then here's the role reference for secret reader. The funny thing is that once you've bound somebody to a role, you have to remove the binding and re-add it. You can't change it actually on the fly. So you have to remove it and then rebind them. So attribute, again, kind of diving into this a little bit more detail, is like we can either match a group, a username, we can control the API group, we can control the namespace, we can set resources, which can either be pods, deployments, services, stateful sets, and then, you know, like non-resource path matching properties that says, you know, like, is it a version that we need to match? Is it like an operating system? Is there some other non-resource path that we need to match? And then of course, read only true or means that they only get to like get read operations. So just know that you don't really see read only false, by the way. Here's some examples. And I think we saw this before, right? Bob, who is specified here as a user, and only the Project Caribou namespace has read only access to these pods. Okay. That is attribute based. By contrast, again, diving into the role example, where's the role examples? Here we are. Here's a role binding. What we're doing is we're basically defining a role. So here's a cluster role, here's a role. And what we're saying is that with this role in the namespace marketing, we're going to call it the marketing pod reader. We are granting them access to pods, and they can actually do the following. They can get pods, they can watch pods, they can list the pods. Get, by the way, means they can read the pod information. They can like describe them as an example. Watch them means they can actually watch the pods to see if they're up and working. List means they can list all the pods on the system. Cluster role, same thing. Get, watch, and list. Now note that you don't need a namespace with cluster roles because you're not limiting someone to a particular namespace. If they have a cluster role, they can do this cluster wide. If they have a role, they're going to be scoped to a particular namespace typically, or a series of namespaces. Just depends on how you want to set it up. And then the binding, whether it's the role binding or the cluster role binding, is what it's used to bind the role or the cluster role to the user, like a respective user. And the list of subjects that could be part of a role binding can be a user, a group, or a service account. So you can create users and groups and obviously bind to service accounts, right? So you can bind a cluster role using a role binding, but it's going to be bound just to that particular namespace. If you want to apply a cluster role to all of the namespaces, you need to do a cluster role binding. So just to be clear, if you want something to grant permission to someone to all the namespaces, you typically want to use a cluster role binding. If you want specific namespaces, even if it's a cluster role, you can use a role binding for that. Let's see, I think we looked at this example already, but we got a user, Alice. Note that the subject could be a user or a service account. and we are binding this particular role called pod reader to this user. This allows the, and it's not, this is not right. This says the default namespace. That's wrong. It actually allows them to read pods inside the sales namespace. Here we got cluster role binding with a group, right? So this is bound to a group. The group name is manager, right? So it's a manager group. So anybody who's a member of that group, by the way, will get this role assigned to them. And then this is a cluster role, and they are called a deployment reader. If we go look at the cluster role definition, I bet you that deployment reader only has get, list, and watch for the deployments, right? Notice that because this is a cluster role, they can do deployments in any namespace. So no namespace restrictions for cluster roles for a cluster role binding. Let's see. There is, oh, that's right. There is a special purpose authorization mode that allows kubelets to like schedule pods, right? If you want to learn more about this, you actually have to read the documentation. It's actually remarkably deep. The other authorization modes, so there's node, there's ABAC, which we talked about. There's RBAC, which we talked about. You can obviously enable ABAC as needed. Most people are using RBAC for their executions. They're not using ABAC, at least that I've seen. Now, after you get authenticated, and then you're authorized, so you're authenticated with the authentication modules, which again is part of the certificate chain, then you're authorized either through ABAC or RBAC. There's also that special node one, which is really only used by the kubelets, right? You then have to go through the admissions controller if it's turned on, which most of the time it is. So after authorization, it's going to go through its final stage. So the admission controller is going to limit requests to create, delete, modify, or connect to a proxy. They do not support read requests. For example, a mission controller module may be used to enforce the pulling of images policies each time a pod is created. So there are kind of a couple of emissions controllers that are at play in the API server binary, right? They're worth considering. Here are some of them. Always pull images, certificate approval. So like when this, like different admission controllers, like pieces can be enabled. And so when, for example, always pull images is enabled, when this admission controller is active, images are always pulled before starting containers, which means, of course, valid credentials are required. So pull image secrets, right? There are a number of admission controllers inside the documentation. So it's a piece of code that intercepts requests to the API server prior to like the creation or persistence of an object, but after it's authenticated and authorized, right? So controllers comprise this particular list, right? So for example, there could be ones like always admit, always deny, always pull images, certificate approval, make sure that certificates are signed, restrictions on subject, which controls name, default ingress class. There's a number here. Admission controllers are incredibly powerful. Usually by default, they're usually turned off, right? There's only like a few that are turned on. And of course, you can also very easily hurt yourself, and you can write your own custom admission controllers if you want to, like if you want to authenticate or hook into another third-party resource. So way beyond the scope of this class, but you can do everything from rate limiting events, making sure that resources aren't exceeded. There's a ton in here. Limit Ranger, that one, the mutating admission webhook, that one's used quite a bit actually. Checking to see if a namespace exists, restrictions on nodes. Yeah, proficient volume claim resize. There's a bunch. Pod security is a pretty standard one. Pod security policy is also another standard one. Anyway, there is a lot here. So this is the admission controller. So remember, it goes authentication, authorization, admission controller, then object, whatever, manipulation, creation, right? Any questions about these stages here? Where was that? Here. Oh, one thing I was going to look up actually. I'm going to show you the authentication. Let's see, there is a list of authentication modules that you sometimes refer to as authorizers. So Bootstrap tokens, service account tokens, Open ID tokens. Yeah. Let's see. Not listed here for some reason. There's the strategies, service accounts. Sorry, just scrolling through for just a second. For example, here's an example where they're using an OIDC authenticator. So they're actually enabling an auth provider of OIDC, setting up all the stuff to make that happen. Here they're using a token option for authentication, webhook token. So just know they're very deep topic. Usually most people will federate authentication into a third-party provider, and they'll use RBAC with the provider to control like roles, cluster roles, bindings along those roles. Most people are not using ABAC anymore. And then they'll turn on admission controllers for enhanced security, which is very custom depending on what you're looking for.
So when we, like, let us say I have a Kubernetes cluster managed by Rancher.
Mhm.
So as long as I copy that, kubeconfig file and put into kubes/config. So it allows me to do all the kubectl commands. I'm wondering where is this RBAC being set for me?
So what's happening is that Rancher manages all the clusters that it talks to through a service account that it inserts into the cluster. So if Rancher has 15 clusters, it's inserted a service account into each of those 15 clusters. When you download the kubeconfig from the Rancher interface and then weave that into your kubectl configuration, what's happening is that, especially if you're going through Rancher, but if you're talking to the cluster directly, what's happening is that you're actually talking to it using that service account, which is an RBAC setup. And so usually that service account is set up as a cluster admin for all the accounts that Rancher manages. So Rancher handles all that for you. And it's not actually like in a sense a dedicated user, it's actually a service account that they're giving you access to.
In fact, at work we we use a key cloak for and the cert, like PKI cert issued by a certificate authority to authenticate.
Right.
And then they have done something for the RBAC so that, for example, the same Rancher has, if he's hosting or managing multiple clusters, which cluster you get access to. So that is, I'm not sure how they do, but something is done so that you access only the cluster you are authorized.
So probably what they're doing is that once you authenticate with Keycloak, it returns like, for example, a user ID, which is then associated with the group using RBAC inside the authorization section. So then that way they can authorize you on a per group basis. Like if you're a member of cluster group 1, then you have access to cluster 1. If you're a member of cluster group 2, you have access to cluster 2. So that way they can make you a member of many different groups based on what comes back from Keycloak.
I'm sorry, if one was not to use Keycloak, and if I was to use, let's say, I still want to use Rancher and Kubernetes cluster on Rancher.
Mhm.
but without using Keycloak, what would be the approach? If I was to host multiple clusters into multiple namespaces for different teams.
Well, it depends. Like you could actually create a role and assign that role, for example, to a group, or you could create a cluster role if you wanted, admins to administer all the namespaces in each of the clusters. And then you could create users inside Rancher, for example, which would then bind through a service account to all those things. So Rancher would then become your user database instead of using another one. Rancher has the ability to actually host its own user database, unlike Kubernetes, which doesn't really do that, right? So in that case, you would actually just use Rancher's integration with those clusters to get you access.
Gotcha. Excellent. Thanks, sir.
Yeah. It does actually run a MySQL database typically on the back end. So that's where it stores all the users at.
Who, the Rancher?
Rancher does, yeah.
Oh.
Yeah. In newer versions, there was talk of pushing that into etcd, which either way doesn't really matter, right? As long as it's stored somewhere.
Yeah.
So yeah. Good. Other questions? All right, so then let's talk about network policies. So if that whole chain of authentication, authorization, and admission controllers allows us to control user authentication into the system, what about network traffic? So that's all API calls that we just talked about. What about pure network traffic? So network policies are basically firewalls that specify how pods are not only allowed to communicate with each other, but also with services and how the outside world is allowed in. So, when you apply a network policy, you can apply selectors on it, like label selectors, so that the policy only applies to certain pods. When the policy is applied to it, then the firewall kind of wraps itself around. It basically changes the network rules inside Kubernetes based on what the policy defines. This is very, very contingent upon the network driver that you are applying to your installation. So like if you're using like Calico or Cilium or Flannel or, right, there are so many network drivers, and there are different kind of pod security policies or network policies that can be applied to those all different types of network drivers. So the policy, by the way, will specify who's allowed in and what's allowed out connections, right? And that, can be covered either through services or ingresses. It also basically defines how pods are allowed to both output and input as well. So network policies do require a network plugin, which is what I'm talking about, the CNI, or basically not CNI, but like a network driver, if you will, kind of like similar to the storage driver. So like Calico, actually says it right there. Calico, Cilium, Romana, WeaveNet, KubeRouter, Tigera, like there's a bunch. Which policy, like which plugins do you use for network? That really depends on what your security team has approved, what environment you're in, and what attributes, like what features are you looking for. You kind of have to experiment to figure out what works for you. Here's an example where they have applied policies to like isolate pods so they can't talk to each other, so we can actually like lock them down. Either allow or deny internet access for pods, allow pod to pod communication within a different namespaces, which typically doesn't happen. Maybe control access from ingresses or services as well. Notice that StackRox is one of the GitHub links on the bottom. So you see some network policy examples. StackRox is a container security company. That was one of the ones that got bought by Red Hat last year.
The network policy is similar to like network access control on like a EC2 environment in a VPC environment.
Yeah, actually, that's not a bad way to think about it. It is very much IP based, and you can basically create allow or deny rules based on the source, destination, and type of traffic. Yeah, it it can get really involved. So just like NACLs can.
Yeah.
Here, by the way, is an isolated pod, and what they're doing is they are basically all right. This is the default denial policy, right? What this means is that it's only going to allow connections that are explicitly listed by other policies. Because if you have an explicit allow, it will actually allow you to do it. But this is like set as a default to deny all policy. Now, this is an arbitrary name, but notice it's basically selecting all pods, and the only thing it's allowing is ingress policy types. Here is internet access for the pods in question. So network policy, once again, arbitrary name, internet access. Here they're selecting a matching label where networking allow internet access equals true. So some of these pods have been labeled basically. Policy type is ingress, and what they're doing here is they're basically allowing all traffic from all sources for pods that have this matching label on their label set.
So ingress means like, is it a allow all?
Yeah, so there's nothing here in this like section here, which means allow everything.
So what is ingress?
It's basically inbound traffic. Right? Ingress and egress. Here's another one. Here's another network policy. Allow ingress, oops, from new. So we've got a pod selector, which basically is choosing everything. Policy types ingress. Ingress where the networking equals true. And then, oh, there's something missing here. I think there's a line missing. Hold on. Network policy allow ingress new. True ingress. There's a line missing. Oh, there it is. Pod selector. So basically this says, if you create a new deployment, they won't be able to talk to anything by default until you apply a network policy. So you can create custom network policies that allow pods labeled with this allow all connections to talk to other pods in the same namespace. So what this is doing is this is saying where any pod that was selected for this, like you can basically allow ingress any traffic from any pod. This is very subtle. Let me back up here. Just want to make sure this is clear. This is not limiting traffic from any source. It can be basically, right? It can be anything out there, right? This basically allows traffic from any source, right? For ingress, incoming traffic. If we look at this ingress, and I wish it wasn't split on 2 pages because I think it's going to confuse you. This is saying, look, instead of like limiting it to any traffic, we're going to allow traffic that comes from any pod. Because it's not limiting the pods. It's that those little like curly braces basically say anything, any match. And so in this particular case, it's going to allow ingress traffic from any pod that has any label on it. Did I mention that security was harder on Kubernetes? Okay. Now let's go take a look at some more network policies because that barely scratched the surface, right? Actually, you know what? Let's go look at StackRox's network policies. I haven't looked at those in a second. StackRox network policy examples. Good deal. Let's go take a look at GitHub. All right, network policy examples. Ooh, where are you? There we are. You're at the very bottom. Haven't updated in a minute. God, 3 years ago. That's horrible. All right, so let's look at some other policies. So here's the default deny policy that like we were just looking at as an example. Notice it just, it says ingress is, you know, the policy type is ingress pod selector, but there's no like definition of like what's allowed, right? It's not defining any ingress, right? It just says I'm a policy that allows ingress, right? Let's go back to this. notice that this matches everything. This says everything is allowed, has an ingress. If we do this, nothing is going to match the ingress. So nothing's going to be allowed. Like there's no pattern matching there. Basically says nothing's allowed. This is the default deny. If we go out here and then look at, for example, internet access, which is the thing we just looked at, notice the policy type is defined, and then we've added this ingress definition that says anything. This little piece right here will match, is just like a wild card. Just think of it as a wild card. And then let's say we're going to allow a server to access. Let's see what this is. So this says we're allowing server to access equals true. And they're going to allow traffic in from where the pod matches the app equals server. So in other words, where the label app equals server matches, they'll allow traffic into any of pod that has this policy applied, as long as app equals server. Allow traffic from the same namespace. So pod selector allows same namespace ingress from where pod selector equals anything. So that's basically notice the pod selector is there, just selecting anything from that particular namespace. And then where is it from namespace 1 to namespace 2? Okay, so this one, pod selector matches label where app equals sensor, ingress from. Here's the namespace selector. So not the pod selector, not a label selector, right? But where the foo bar, like the namespace has the match and app equals server. So the namespace has to have a label where foo equals bar for these namespaces to all talk to each other. Let's see database access. So where app equals DB, we're going to apply this pod, this policy, where networking allow DB access equals true. So that would actually have to be on the pod itself. So you can see where labeling becomes really important if you're going to try and control access, because you're going to have to put labels on here that are going to trigger these policies to apply themselves to. This is a deep rabbit hole to go down, but just know that this is a whole dedicated course of study in itself as far as the security goes. Do note that you do have to learn what all this syntax means as far as this is confusing to most people. Like, what does that actually mean? It means wildcard. Any traffic can come in here. By default, by the way, when you wrap a policy around a pod, it typically denies all traffic, right? So you then have to start opening it up in order to grant it. You can change that behavior, but typically it denies all traffic until an allow is set up. So it's kind of an implicit deny, and then you explicitly allow traffic into the pods that match the ingress policy. Now, that may seem a little confusing. So why don't we get hands-on on this and actually drive this home to see if we can actually understand this a little better. So we're actually going to move and talk about RBAC security, which is the next thing we're going to touch. I don't think we actually have a lab on policies because they are just complicated, right? But here's what I want to do before we actually start this lab, is that it's actually 5 minutes before 4. And so I know we did some labs and then we did some lectures. So we've been going for about 2 hours and we've got about 2 hours left. So what I'd like to do is I'd like for us to take a break, actually. So it's 3:56 right now. Why don't you come back at 4:15, hold your questions, just remember them, and then I'll answer any questions about the pieces in question, and then we'll move on to the lab, okay? All right. I will see you in just shy of 20 minutes. Welcome back, everybody. Okay, so any questions at all for anything that we covered around authentication, RBAC, ABAC, emission controllers, network security policies, just really the tip of the iceberg around security for Kubernetes. Most consumers, like who deploy applications onto a cluster, are not going to manage the roles. They're not going to manage authentication and authorization. Remember, this is an application authentication authorization. This is just for access to the cluster. Most developers slash, testers, whatnot, running applications are not going to be administering network security policies or pod security policies. Okay. Well, then let's do a little bit with RBAC just to get a feel for how the role binding and the cluster role binding starts. So we're going to do lab 7. And note that you are actually going to make a security directory, right? And then you're going to copy the lab files from security into that directory. Probably helpful if I did that. Then you're going to take a look at your own kubectl config just to see your connection to the Minikube cluster. Oops, don't do that. And then you're going to set some credentials in your kube config. You're going to set password, right? Using like a new principal based on kind of like what you have to possibly set up. There's now going to be 2 users, right? So there's going to be the Alice user with a plain text password, whereas the default user was added with basically a certificate, right? Then you're going to create a another user and principal, and this one's going to be called Joe. This time you're going to be using a key and a certificate, right? You're going to run the following commands to generate using OpenSSL to generate the key request. Just so you know, by the way, OpenSSL commands do figure on the CKA exam, so they do show up quite a bit. And then, sorry, I'm going to create the new
kubeconfig file. Is it going to be available only on the etcd, or is it going to be available on every node or every pod?
The kubectl file is only available on the client.
Pardon me?
So it's only available wherever you're running kubectl at.
Okay.
It's not on it's not on a server.
It's a product. It is based off of one cluster, Sean. So for one cluster, you download that kubeconfig file
Okay.
and put it in your local directory on your local machine and then machine where you're going to be running the kubectl from.
Yeah, so for example, on my system here, I have a config file that contains references to certificates and other things. And so if I wanted to run it on another system, I would need to grab the config file plus the relevant certificates and copy them over to another system. That's where it gets weird, right? Because for the most part, even though it can mimic it, Kubernetes uses certificates and keys to actually authenticate against the cluster. So you have to enable some other kind of mechanism if you want to authenticate through other third parties, like username and passwords for the most part. So it only exists locally. So here we're actually going to generate another certificate signing request for the private key. And then we're going to create a variable, store the location. And then we're going to generate the final CRT by approving the certificate signing request, the Joe CSR that made earlier. And you're going to look at the certificate content. Then you're going to create a principal using the certificate that you generated. And then you're going to actually set credentials for that. Right? And then you're going to create the context so you can actually switch easily between users. You're going to create some namespaces and create a deployment and then set a context for that particular deployment. set of context for Alice here as well. And they're going to do config view, and it's going to show you different things like different namespaces that you have actually set up these different users for. And it's going to show you the current context. And then you get some deployments where this n equals sales. That's interesting. And then basically set yourself as the Joe context, so you can actually run the kubectl command by switching contexts in line without really kind of officially switching your contexts. They're going to explore some of this, get your deployments, and then you're going to switch back to the Minikube context, right? So you can actually switch it back. And then see if you have the ability to access the sales namespace. So these commands are going to actually allow you to test your permissions, switch contexts, assume context in the middle of a command. And then you're going to keep on going by basically authorizing a user to access a particular namespace. So you're going to look at the contents of this particular file and then apply the particular RBAC that's created here, get your roles, read the role binding file, which is also submitted for you, apply the role binding, get your role binding so you can actually see how they work in the sales namespace. And then you're basically going to get pods as Alice, get pods as Joe, switch contexts, create some deployments, and then just see how all of this works, right? So what you're really looking for is you're creating segmentation using namespaces and users that have access to those different namespaces. That's basically what you're doing. And then we're going to create a deployment manager role and then role bind that role in as well. And then we're going to use the Joe context to test it, perform another deployment, delete the old deployments. And then we're going to do the same thing, but this time we're going to use the cluster role and we're going to basically apply it. And then we're going to look at the cluster role binding, right? And we're going to apply the cluster role binding as well. And then you're going to test that as Joe and test it as Alice. Now notice that Alice is not going to actually have the cluster role assigned, so she should not see anything. And then you're literally just going to clean it up. That's really all you're doing. You do not, by the way, have to do the Minikubes deletes and Minikube stops. So you don't necessarily have to stop the cluster. Okay. That 9-parter basically is all going to be lab 7. Okay. So that's where we're going to be focused. This lab can take a little bit longer. So, let's see how far we get, but this lab usually takes upwards of 45 minutes. So at a minimum, we'll be checking back in usually around like 5:05, 5:15 or so. Okay. So I'm here to answer any questions. Let's go ahead and get started on lab 7. And let me know if you run into any issues. Do note, by the way, you're going to be powering off 3007 and you will be starting up. I'm sorry, you're going to be powering off 2675. You're going to be working on 3007 in here. Okay. Yeah, thank you for the reminder. So, this is one of the modules from the official course about networking. So, there's a little bit of context setting here, but basically, let's just talk about how networking functions, because this is how it works for most locations, right? So you don't necessarily need to know AWS fundamentals. The main thing that you need to remember is that we are talking about systems that are sitting in an IP range, right? So whether it's a private IP range or a public IP range, that's your discretion. You figure that out, right? And we do this all the time at home because this is how our routers work typically in our house, right? Because we have private subnets. So that's not necessarily as important, but it is worth noting that this is a 192.168 range, and this is a 1 range, and this is 64, and this is 65. So whatever the range is, it is important to note that that is actually the range. Now, in like AWS parlance, there's a device that acts as a gateway and then a device that acts as an internet gateway. In our homes, that operates a little bit differently, right? So as far as like private and public subnets, that's a discussion for AWS. Just know that most of us in our homes, we run private subnets, and when we run Kubernetes, typically Kubernetes is actually on a private subnet. It's not on a subnet that has, like, it can get to the internet, but it's not necessarily like exposed to the internet directly. More on that in just a second. Let me scroll past this really quick though. All right, but the thing that to note is that how does container to container communication, how does pod to pod communication, and how does ingress into the cluster work? Like that's what we're really talking about when we talk about Kubernetes networking, right? And so with intra like pod communication, if it's just like, you know, because what happens is that Kubernetes is going to treat pods like virtual machines. So let me say that again. Kubernetes is going to treat pods like virtual machines. It's going to give them an IP address. It's going to note the IP address. It's going to have a name for the pod that you can actually find in DNS. It's going to load balance if there's more than one. And it's going to allocate ports to that pod, right? So if you punch a hole in there and say, I want to make sure this port is exposed, that's what's going to happen. Containers in a pod basically share the entire namespace and can communicate with each other using local hosts, right? So there's no natting. They're just going up and down the network stack. So they basically use ports to talk to each other. So all the containers talk to each other on ports using that same networking stack. They can use local host. You could have one bound to port 8080, another bound to port 80, another bound to port 443, like, and they're going to talk to each other through that same stack using ports. Same IP address. So that's container to container communication. And in case the drawing is confusing, this is a container and this is a container, and it's talking to it. They're talking to each other. Notice they are not leaving the boundaries of the pod. Right? Now, notice that this has an IP address, the pod does, and notice that the host has an IP address too. Notice that this is a 1 and this is a 74. So they're not even really on the same networks depending on how it's subnetted out, right? So just noting that, okay? Now, let's say we're on the same host, all right? So this is one box right here. So this is intra host. And you've got basically a container up here who wants to talk to a container up here. Note that this is like a user namespace up here. So this line, this is what this line is delineating. And so when this pod wants to talk to this pod, what happens is it comes down out through the pod, like the virtual interface, hits, basically what's known as the virtual bridge that Kubernetes has, comes over through the bridge to the other interface and goes right into the pod. Now just note that these pods actually do have distinct IP addresses, and that's how they find each other. Let me say that again in case you missed that. These pods each have distinct IP addresses, and even though they're not leaving the host, this is how inside the host they can find each other. VMware, by the way, does almost the exactly same thing. There's a virtual bridge down here, and it will route internally into the host without ever touching the network card of the host in question.
So you are saying both the pods are in the same host. Does it mean is it in the same node?
Yes, that means the same thing. Host and node are synonymous.
Okay.
Yeah. So it's hitting going out the pod interface, hitting the virtual bridge, hitting the other virtual bridge, because this one, there's a routing table here that knows the IP addresses, and then it's going to go up here, right? And then, by the way, it's going to hit the port. So whichever port was specified is going to determine which container it hits. Okay. Okay, so that's inside of a single host. You got two pods talking to each other. What about what happens when we've got hosts we got one pod talking to another pod and they're on different systems. So let's say it's this pod wants to talk to this pod. How does that happen? Well, note that the pods themselves, right here, obviously all have this, these IP addresses. So we're taking our previous diagram and we've kind of microsized it. And now we're adding the IP addresses. Notice that this is actually coming down to talk to this virtual kind of interface / bridge. It's going here, going here, going here, hitting this, right? Note that 194 and 195 are advertised on the actual interface for the host, but that's for somebody coming from the outside in. Otherwise, for our purposes, since we're still staying on the same host, that traffic does not need to talk to the network interface for the host. It can literally just stay right there. So we're still intra-host. We haven't left the host yet. Now consider this one where we actually want to talk to another system that's on another host. So let's say this one, as an example, wants to talk to this one way over here. So notice that this is 195. This is a 2.195, and this is a 1.94. What happens is that this container is going to go out through this interface, hit the virtual bridge. Notice that, by the way, these two have the same IP address. Then it's going to hit the network interface. And since it knows that it's looking for 195, 2.195, it's going to go out to this advertised address, come in through the network card, which is then going to redirect it to 2.95, and then it's going to redirect it to the actual pod itself. In part, this whole thing that you're looking at right now is the reason why it's hard to get more than 200 pods onto a node. It's not a resource problem, but imagine if you have 200 IP addresses down here advertising from a single network card, right? This is why in Amazon, you have to add network cards if you want to increase the number of pods that are on the system, right? Because it's not a problem with total amount of memory and CPU. It's a problem with the number of advertisements that can be made across a network interface, right? You can get too chatty somewhere. That's one problem. There's actually other resource constraints, right? But hopefully in looking at this, this makes it really clear. Here to here to here, just that simple, but only because the IP address we're looking for is being advertised by this network card down here. Can you imagine how weird this could get if you wanted to troubleshoot it? It could get a little crazy. So that's how a host talk to each other. Now, you're like, Michael, that sounds great. Good job. Thanks for explaining that. How in the world does this work if someone's coming from the outside in, right? Because these guys are all talking to each other. What if I want to come from the outside world, or what if I'm internal to the cluster and I want to do load balancing or whatnot? How does that happen? Okay, stick with me. Remember, I said networking and security are hard, right? Okay, so now that you know how pods and containers communicate, let's talk about how services work in order to load balance communications with all the different pods, right? So services solve the issues of pods disappearing and being added and moving around on different places, because new pods are created all the time with different IP addresses, right? So instead of trying to communicate with the IP address of pods that are constantly moving around, you communicate with a service. The service has a static IP address, and it is tracking all of the pod movements on the back end, because every time a pod starts, it registers itself with the service, kind of like service discovery. So this provides a consistent IP address, and port has an entry point into a group of pods. Each service has its own IP address, and the port does not change for as long as that service exists. By the way, you can route a service that's advertising port 80 to a pod that is surfacing a web server on port 32,000. Now, here's the catch. And Sean was asking me about this earlier, and Vinod was as well, right? Is that like cluster IP addresses are for internal use only. So if I have a number of pods on the back end here, and I want to have a single IP address that can refer to these, well, this is literally what a cluster IP is for. So for example, if I have an app set of pods that need to find a database that's running locally on the cluster, literally all I would do is I would come out here and I would basically create a cluster IP address. And what would happen is that cluster IP address would lead to, let's say this is an Elasticsearch cluster, it would lead to all the nodes in the cluster. Or, you know, if you had client nodes, you could do that as well, right? So that's just a cluster IP. The only people who can access a cluster IP is someone who is on the cluster. That's it. No one outside the cluster can get to the cluster IP address. Now I know, like, if you just saw the exchange that I was just having, you were kind of like, well, hold on, Michael, we just hit a 10 address and we were Minikube in Docker mode is not the same as running a production Kubernetes cluster. So just like roll with that, unfortunately. Minikube tries to make it really easy for you to get to services. So just ignore that, right? That's not how it works in real Kubernetes, right? Now, here's the funny thing. This service type of the cluster IP, because these are all service types. There's the external name service type, the load balancer service type, the node port service type, and the cluster IP service type. These are all just service types, right? Now, what's funny about this is that we use these service types at every level. So for example, if someone comes in and says, hey, Michael, can you run a service type and I want you to use a node port? And what that means, just to like spread that out, is that means that every node would be bound with like a port. Oops. So let's say I have 5 nodes, they would each be listening on this port. And if I hit that port, by the way, what's going to happen is that that port is going to get redirected to the cluster IP address, which is then going to redirect to all the pods behind that cluster IP address. So let me draw that just slightly differently. Oh, that's not what I wanted. Hold on, let me do that again.
Do all those ports need to be different? Can they be the same?
Well, you are right to ask. Why, Hardik? Why do you ask? Because I think you know what the problem is.
Because if it's the same port, I wouldn't know where to go.
Well, here's the funny thing is that if you hit, it's going to try and bind this across all the nodes in the cluster. Now, as you can imagine, if somebody else has that port, you're not going to be able to bind it, right? That can be problematic. So node port is not an awesome way to get to a bunch of systems. Like people don't like it because you can run into collisions, right? So let me just do this really quick to set up my little pods. Okay.
So
Does that make it?
People from outside, they reach the load balancer, which then directs to the node and then to the cluster? Or
not talking about load balancers yet. We're not talking about load balancers yet. Just so hold on for just a second, right? We'll get there, I promise. Now, so when they come in and hit the node port traffic, that's going to hit the node port, which then is going to direct them to the cluster IP. Cluster IP is going to then talk to the systems in question, the pods in question, right? Now, let's go to what you were just talking about, right? So let's go where all of a sudden we have decided to add a load balancer into the equation. Now that load balancer could actually be a network load balancer or some other external device. But for giggles, let's just say that the load balancer is, you know, a virtual device that's part of the Kubernetes cluster. What happens here is that when we hit a port on the load balancer, it's going to redirect to a node port, which then redirects to a cluster IP, which is then going to hit the pod. So it's literally going to go load balancer, node port, cluster IP. if you add an ingress, which is very much typically a separate device, that's going to hit the load balancer, which is going to hit the node port, which is going to hit a cluster IP address. So the load balancer, which is usually the load balancer is exposed externally with your like cloud provider's device. So if the cloud provider has a load balancer type, that's usually what happens. That's the same with ingress as well, by the way. An ingress is usually an external device that's used, although you can run ingresses on your cluster if you want to. You can stack everything on your cluster if you want the cluster to handle it. So just note that it actually runs to load balancer to node port to cluster IP. External name, by the way, just goes out to an external name. So it operates just a little differently.
A question, sir.
Yeah.
Could you
Go ahead.
undo that one? The one or no?
Actually, I did that on accident. So I'm just going to type it again because I've gotten really good at that.
Oh, you did.
Yeah. Yeah, it's okay. Go ahead, ask your question.
I was gonna ask, so in that diagram here, the one that if you were using the ingress, right? So from ingress, you were coming to load balancer, then node port, then cluster IP. Sir, this load balancer here, so there is, as you know, or as you taught, there is a load balancer service Kubernetes service object.
Right.
And then there is this physical load balancer from provider, for example.
Right.
So the one that you are showing in this diagram, that's like obviously on the Kubernetes, that's your load balancer object. But
Right.
is this, where would be the, where in this diagram, if we were to kind of annotate or somewhere mention that physical load balancer, where would that be?
So it could also be outside if you wanted to, and then it would talk to the node port, which would talk to cluster IP address, which would do this.
I see. So if you're using ingress, obviously we need a load balancer to route traffic to ingress controller, right, sir?
Well, the ingress can be an entry point, right?
Yeah.
So the ingress can be an entry point, which can also go to a node port, which can go to a cluster IP, which can lead on, right?
Yeah.
Right. So in all cases, at the very least, it's going to use node port and cluster IP to get in. Whether this load balancer is here, whether the load balancer is actually provided by the cloud provider as a virtual appliance, or there's an ingress here, that's discretionary. But you are going to use node port and cluster IP to get that traffic back to the pods.
Yeah. But if you're using ingress, then I should be able to route using the ingress object in the Kubernetes cluster. I should be able to route traffic from ingress to cluster IP directly, right? So then we don't need node port, do we?
So you can actually force the ingress to go past the cluster IP. I believe that most of the setup
Even
sites
past node port?
Past node port, yeah. So past node port, sorry, into the cluster IP address. But the problem with that is that I don't think that's actually officially released yet. The problem with that is that the cluster IP is not available outside the cluster. So you have to hit a node port. You following me?
So you see cluster
ingress
IP
can't talk directly to the cluster IP. The cluster IP is only available for objects that are inside the cluster.
Yeah.
So you have to hit the node port.
Oh.
Right? Because you can't hit the cluster IP from outside the cluster. So if your
But
ingress
I thought
object
that-
is outside, then you have to go into the cluster, into the node port.
So I thought that we did some proof of concept recently where we set up, in ingress controller. Obviously, ingress controller is running, Nginx ingress controller was running on the Rancher cluster.
On the
Kubernetes
cluster, which is different than out of the cluster, right?
Correct. Yeah, it was running on the Kubernetes cluster.
If it's on the cluster, it can talk to the cluster IP address. If it's outside the cluster, it has to talk to the node ports.
Gotcha.
Right.
Yeah. So
Yeah.
the ones that I was referring to is that the ingress controller is running exactly on the same Kubernetes cluster where the pods are running.
Yeah, exactly. And like Minikube, for example, has the ability for you just to enable an ingress controller, and it starts Nginx on the cluster and it talks to the cluster IP address.
Gotcha.
But if you're coming from outside, you got to hit a node port.
Yeah.
Yeah.
Thank you, sir.
Yeah, that's a good point of clarification, and that usually comes up actually. So yeah. Hardik, to your previous statement, yeah, you got to be. It's going to try and randomize the ports, and if it finds that the port is bound, it's going to choose another randomized port to kind of do that, if that makes any sense. But it's got 32,000 ports to choose from to expose a node port across the entire cluster. Because the range it'll choose from, I think it's like 32,000 to 65,000, if I remember correctly.
Okay, got it. Thanks.
Yeah.
Oh, can the ingress controller in this diagram, you said it can also be in the cluster too?
Yeah, so sometimes instead of running it outside the cluster, if you enable like Minikube, for example, has a bunch of add-ons that you can turn on. One of them is called an ingress controller. It will take Nginx and it will literally run it right, not that, it'll run it right inside the cluster. And so what will happen is that because it's inside the cluster and it's a service, like it's like a pod inside the system, what it can do is it can literally just talk directly to the cluster IP address.
Is there any disadvantage of doing that, or what's the best practice usually?
Usually the best practice is use node port still, right? Because then that way, if it's like, then you've got it spread across the entire cluster. Anybody who hits that port from any point can actually get to the cluster IP address. And that's the same for the cluster IP address. But if you then decide later to externalize that load balancer, or you want to externalize it in some way, it's more secure to talk to the cluster IP address, but it's more available if you can talk to the node port. So actually, I kind of like confused myself there, because I was like, actually, it just depends on your use case, right? In general, I prefer to just run through the node port, but most of the setups that you find from Helm and whatnot will actually have it talk directly to the cluster IP address. So, but my preference is node port. So, but I also tend to have a firewall around all my stuff, and so I'm not like super concerned about people getting into the cluster, but that's not necessarily best security practice. Best security practice is to talk to cluster IP. So I guess really the answer is it depends.
Yeah, I think that if you were to do like a path-based, routing, and let's say you have multiple applications running on the same Kubernetes cluster, listening on different ports, then and if we have this ingress controller inside, I think then ingress to cluster IP, at least that's what we found was better, instead of opening node port on every worker node. And having said that, since ingress controller is now running inside Kubernetes cluster, the question is, how do you bring the traffic from outside, right? So you still need a physical load balancer. So we have what we did, I think, or some geniuses at work did, if I understood correctly. I may be off a little bit, I may be wrong. So we have this what you call physical load balancer, like a AWS physical load balancer. And then we created like some DNS name with CNAME, mapping some host name with this load balancer, physical load balancer. So it's a physical load balancer that is bringing traffic to this, to the what you call these. I feel like saying ingress controller, and but ingress controller, as you know, listens only on 2 ports, right? Like 80 and 443.
Yep.
So,
it's only for web
that
traffic.
way you can bring secure traffic to your environment, like, and without opening any node port on every worker node. Something like that, I think, because there were some issues. I mean, obviously node port allowed you to, get inside, but for people were not comfortable opening node port on every worker node. But they're okay to open, 80 and 443, and they don't allow you to use 80. So 443 means you have to, have secure traffic.
Well, and I have seen it basically with what you're describing, where the ingress controller talks to a load balancer that's on the cluster, which then goes directly to the cluster IP address. And then you don't have to do node port at that point in time.
Something like that. Yeah.
Yeah. And so, that's definitely possible. But, like Amazon, for example, will run an application load balancer, then a network load balancer that is not on the cluster, and that still talks to node port. So, I mean, there's a bunch of different ways to approach this, but did I mention that networking is hard on Kubernetes? Have I mentioned that? So, and the problem is there's a lot of flexibility, right? So that's the challenge. But just clearing all this out for a second, right? Just know that when you run something like a load balancer on the system, it is typically going to talk to load port, then to cluster IP, then to pod. So there are ways around it. You can jury rig it. You can externalize load balancer off the cluster if you want to, but typically node port is going to be active unless you change it to be not active. Sorry. Got distracted there for a second. So just know that that's typically going to be the path of things, but you can change it. Bottom line is though, is the cluster IP is only going to be accessible to anything that's inside the cluster. So you can work from there. Now, opening up node ports, by the way, is not a manual process. So it's not like we have to do it. You just tell Kubernetes you want it and it does it across all the hosts. That's what the kube proxy software is there for. So it shouldn't have been a big deal, but to say this, obviously it might be a security problem, right? But just to say this is that if you run a load balancer on the system, you're going to be exposing that anyway. But to your point is that you were saying, well, we're just exposing SSL traffic at that point. We're just exposing 443 at a single ingress point. So that is a more narrow way to control the vector of attack. Yeah, makes sense. By the way, this is where the like security policies, the network security policies we were messing with. This is where they come in, because imagine if you could open a node port and you would only accept traffic from this load balancer. Right? But then you could expose the load balancer out, but the node ports are actually not accessible by anything else. I know that we were talking about mainly pod security policies, but you can put policies on the nodes as well, like depending on the driver that you use. So just know is that you can actually block those off as well. There's some level of control for that. Okay. Good discussion. All right. Let's just do a quick little visual here that might give us some idea. So as pointed out, cluster IP services are only accessible from within the cluster. When an IP address is assigned to the cluster, as this happened here, right? With that, the cluster service IP is going to route traffic to the nodes. Each node has a kube proxy container. So notice that, right? There's a kube proxy container here, right? And kube proxy is going to create these IP table rules on each of the hosts that says, look, if the destination is 192.74.9, which by the way, matches this exactly. Here's 192.74.9, which matches this exactly. Then I want you to route to these pods that are active on the system, which matches these pods exactly. So I want you to route to these pods on the system. Oh, and by the way, oh, it's not here. They're over here, right? And so this way it lets you basically, if your web app is looking for your back end, this is what it's going to do, is that in this particular case, if the web app is looking for the back end, it's actually going to hit this 74.99 IP address, right? So it's going to route out to the 74.99, and then it's going to redirect itself over to the 192.194.68 in order to get to these systems. Now, traffic-wise, that's going to look like this. It went out here, right? Found the destination, went directly to the other system, and then went directly to the pods. Right? So it's going to go directly to the system in question. Once it realizes this,
the web app address is not in the target. Like, then the target has the other ones, like the backend ones, but not the web app.
Right, because the web app is the one that's trying to get to the back end.
Okay, so the queue proxy is not for the cluster IP, it's for the web app to the backend. Because you know, in the queue proxy, the destination says the cluster IP address, and the target says the backend IP address.
Yeah, so when the cluster IP was created, it actually modified the IP tables to make this happen. So that
Okay.
way, every system, every node in the cluster would know exactly where the targets are. So if you try to hit that cluster IP address, you know where to go to find those the target pods.
Yeah, my only concern is why is the web app not on the target, like on the queue proxy? You know, like when the backend is there, why is not the web app?
Because that's not included in the example. This is just an example. They're not showing us the whole IP tables list, right? They're just
But it
showing
will
us.
also be there, right?
It would also be there, right?
Okay.
Yeah, if you needed to find it. The only difference is that, you know, as far as like service discovery goes, right? That would actually be more in the service discovery DNS side of things than it would be, right, in the like table thing. It's more likely that if you're looking for this IP address, it would say go to this MAC, like host or MAC address, right? So the redirection for like DNS resolution is actually on the DNS side of things. It's not actually in IP tables. Does that make sense? DNS resolution is going to be in the DNS server, not in IP tables, which is actually just IP resolution, IP forwarding, that kind of thing. Okay, didn't hear anything. I want to assume that's a yes. Okay,
So
here
the
by the
web app, in order to reach the backend, it has to go through the API server to the backend, or it has to go through the ENI.
no, if network traffic is just going to go through the ENI. This is just showing that the API server was making change to the kubelet when which made changes to the proxy to add the IP table rules here. Network traffic is going to go through network interfaces.
Okay.
Yeah. Let's see. You can define a cluster IP service, right? Which, you know, this all looks remarkably sane. We've seen this before, right? So great examples if you need to find them on the Kubernetes documentation as well. Notice the target port is listed here as far, and then port 443. The target port is typically what's on the container, like on the pod, like what it's listing for. Notice here that you got port 80 has the cluster IP backend service set up, but notice the target port is 9376. Again, that's what's on the pods that are listening. Note also that the node port service, which is obviously the next layer up from cluster IP address, here we've got external traffic and they are basically hitting like port 32,001. So they're hitting this front end. Now, when the node port service is created, the exact same thing happens, is that when this service is created, it talks to the API, you know, someone's talking to the API server, which talks to the kubelet on all the boxes, talks to kube proxy, and says, hey, if you're trying to get to this IP address, which just happens to be like the host IP address, right? And this port, then we're going to redirect you to these systems, right? And so if you hit 32,001 on any box, it's going to redirect you to the box that has this port available, right? So it's going to redirect you to this system. So node port just redirects from a port and IP address over to another port and IP address. The definition for this is exactly the same. You just set a different type. So it's a node port, you got a web app selector for the app on the back end. And then notice again, right, that the target port is 9376. The node port is 32,000, but you know, that's going to come in, it's going to look like web traffic, right? And then the load balancer service, which is the last one we're going to talk about. Like here's a classic load balancer. That could be a network load balancer, right? This is actually just going to be targeting, right, the ports that are available on each of the nodes in question, right? So here it's going to be listening to 32001, and it's going to load balance to one of the backend pods. So the load balancer service type just extends the node port service by adding a load balancer in front of the nodes. So this means Kubernetes requests the load balancers, and it's going to register all the nodes against the load balancer. The load balancer, by the way, does not detect where the pods are for a given service. So all the worker nodes are typically added as backend instances into the load balancer. And I think by default, I think network load balancers are used for the load balancers type now. I think it was classic. I think they switched it to network load balancer, so it's no longer classic, right? So you can add an annotation, I think, to now force it back to the network load balancer. Sorry, back to the classic load balancer, but I think they switched it over to network load balancers as of now.
That's right.
Here we're defining a load balancer service once again. Notice there's no node port definition because you don't need it, right? Now, if you need more complicated pathing and routing, you need something to read your payload, or you want to redirect based on multiple DNS names against, you know, the same kind of set of services, and you want them to route to different things. This is where an ingress comes in, right? So a Kubernetes ingress object is going to be able to reduce the number of load balancers you're using, because you can then do path-based routing, right? Instead of IP-based routing, which is on a per like load balancer. You have to use a load balancer for each one if you're going to do that, right? So ingress objects are going to use ingress controllers, which are going to like have a bunch of rules and like fulfill the rules and requests through the load balancer. So you can transition load balancer from one service, like having a load balancer on a per service basis, to having a ingress, right? A load balancer per ingress, and then you can use that ingress like example.com to route to multiple services. So instead of /nginx, as that said /desktop or /mobile, right? Or /Americas versus, you know, Asia Pacific or /Europe or /Africa, whatever you're going for, right? There are lots of ingress controller options. You could use nginx, you could use F5, you can use an application load balancer, and it's going to do pathing, right, against a service, right? Notice that service is going to be, right, most likely a load balancer, sometimes a node port. It just depends on how you want it set up. Here, just to show what this looks like, we've got an application load balancer routing straight into a node port, and then it in turn, right, is running into the pods in question. Now, I know that sounds weird, but cluster IP is still actually in play here, right? We're not surfacing that for just for confusion purposes, right? Notice that web app 1 goes to 32,003, web app 2 goes to 32,004. So it's going to pick the proper, you know, app based on the pathing, right? It's going to forward it to one of the EC2 instances based on the node port that's available. Here, notice that you can actually define the paths for the ingress here. So remember, this is going to either be 80, this is going to be 80 or 443 traffic. So you're going to either have HTTP or HTTPS, depending on what you're routing to. And then last but not least is external name, right? So external name, what happens is that, you know, this is external name service. When you create a service called database and you point it to an Amazon like RDS instance, pods that require access to the database are going to connect to that database service. And that service, when they connect to that port, it's going to return the actual DNS name for the RDS endpoint. So this type of service is great if you want to migrate an external resource to the Kubernetes cluster, but you want to access it on the inside, right? So, and by the way, if you decide that you want to migrate it later from external RDS inside, that sounds great. Honestly, I think externalizing your data stores outside that Kubernetes cluster is a lot more stability creating. You define an external name very simply, put it in namespace. Here's the external name. It's going to create everything else that you need, right, for you. Okay. That was a preamble because we're actually going to cover services even more in depth tomorrow. Not necessarily deeper, but we're going to review them. So if all that kind of was like, wow, that's a lot, don't worry. We're going to cover some of those details again in the official material tomorrow. I just wanted to give you a little bit of a preview because using ingresses with load balancers, with node ports, with cluster IP addresses, and then of course using external names, that it can be a difficult concept. So I wanted to give you the night to sleep on it. Okay, questions, comments, anything else to add before we close for the night? No? Okay.
Sir, I have a question, in fact, for the lab, but what you just presented, that's really good.
Sorry, I missed that. What was the last thing you said?
Oh, I'm saying, so like, what you just discussed here for the networking, that's really very helpful.
Good.
But I do have a question on the lab.
Ask
like
away.
So, sir, when I want to go to lab 5, I believe it asks us to use the other machine, right?
The 2675, yes.
Correct. But when I go to my RDP, it seems to be like I don't know how to go back to the page where I have that icon to click.
You have to shut the other one down first. You have to power
Okay.
it. You have to power it off.
I see. So basically I exit out of it, or what do I do?
You go into the terminal and sudo shutdown now.
Sudo
Space shutdown, space now.
down.
I just have one quick question for you.
Sure, Sean, go ahead.
See, so far we saw, fully Kubernetes, like the cluster, we saw the nodes and then the pods, containers and all. So where does Rancher, I'm trying to understand. So now if I do a Rancher Kubernetes, so is it another layer on top of Kubernetes?
Yes, that's exactly right.
So the Rancher also has the HCD control plane, and then in turn inside there is a Kubernetes.
Yeah, so actually I just had to cover this actually the other day. And I don't have the other material, but hold on, let me show you this. So this is what Rancher kind of looks like on the cluster itself, right? So what happens is that Rancher actually sits on top of Kubernetes because it's usually deployed inside of a Kubernetes cluster. And then what it does is it creates other Kubernetes clusters that it is linked to and it controls to a certain degree.
Are you
Now,
sharing anything?
oh, I am actually, and I'm not showing it. So that's not really useful. Thanks for saying something, right? So here, what's happening is that Rancher, you're hitting the Rancher URI or using the Rancher CLI. You can also use the Kubernetes, and you can also create endpoints down here that you can actually use kubectl with if you want to, even if it's controlled by Rancher. So Rancher is usually deployed into a Kubernetes cluster itself, and it starts other clusters like these downstream clusters that you see here, including EKS, GKE, all the stuff, right? And so there's usually a cluster controller that's created for every single cluster that it's controlling. But notice it's using etcd, and if you put it into a Kubernetes cluster, it'll just leverage the etcd that's already there. but then it will start its own API server and it will have its own authentication proxy. This used to be a MySQL database, and I think it still does that if you run it like in a certain context. But this is what it does: is it adds its own components and it extends the Kubernetes infrastructure, like the API. But any downstream that it runs, it actually puts a cluster agent and then puts a little like API server on it as well. And so, you know, it adds its own kind of thing to it, depending on what kind of cluster it is.
So in this diagram, the top portion is like the Kubernetes, what is it, management node, manager node, or whatever. And then these are like the clusters, the worker nodes, right?
Yeah, so notice that there are actual like manager nodes in here, right? You're kind of not seeing them, but they are here. So there are still master nodes inside the clusters that it creates. It doesn't replace the master nodes.
So
They're still
instead of using Kubernetes to create or anything, we are using Rancher to create the cluster, right?
Right. Instead of using like COPS or any kind of other provisioning tools to create your own clusters, you're letting Rancher just create the clusters for you. Right. So then all of these become clusters that Rancher just manages for you at that point in time. And it starts a new controller manager for each of the clusters.
Okay.
Yeah.
So these downstreams are clusters. They are full-fledged clusters. Right? They have the, as you said before, they have master control plane. They have worker nodes, but it's just that Rancher, Rancher happens to be running inside its own, Kubernetes cluster, which we may not see.
Right. And if it's on a cluster, there's going to be a master node and Rancher's going to be running on,
Yeah.
a worker node, right?
Yeah.
And so,
Right.
and like EKS, it's hard because you actually can't see the masters in EKS, which is what this is, right?
Yeah.
And I will tell you that I don't know if RKE, if it actually does launch masters, but every other cluster type, it has masters in there.
Yeah.
So I'm actually pretty sure that it actually does launch masters, because who's going to maintain the state of the cluster? Because Rancher doesn't do that.
Yeah.
Rancher is just a management layer on top of Kubernetes. So I'm almost positive it launches a masters. Yeah.
Because that Rancher, although I said Rancher runs in the Kubernetes cluster, but Rancher, in a dev environment, for example, it can be just a Docker, container.
Right.
And just one instance, and obviously that's going, if it crashes, then you're out of luck. But it can create your full-fledged Kubernetes downstream
Right.
cluster.
It doesn't need to sit on Kubernetes to function. It just needs to be running.
Running, yeah.
Yeah.
Okay, thank you. So see you tomorrow.
Yeah, absolutely. Thanks for the questions. Yeah. So we'll see you tomorrow at 10 a.m. So we'll pick it up from there.
Michael said, can I I think I was able to shut down those machines. And I just want to bring up that machine to make sure so that I could finish my lab. Sir, if you could hang in there for a minute.
Okay.
Thank you, sir.
hold.